Let's talk a little bit about immersive media. But before we do that, let's watch a short video to better understand the different possibilities that we can achieve. Immersive media is getting more and more popular because it bridges the gap between real world and the virtual environment. It also empowers the user. Instead of him being just a spectator, users can now control how they are participating in the experience. A lot of industries can use immersive media for entertainment. This is the main reason I'm interested in the field. But also it can improve creativity and productivity in some fields. Of course, last but not least is usability. You can really automate a lot of manual tasks using things like virtual reality or augmented reality and mixed reality, of course. Let's look at the different factors required to achieve augmented reality. For example, we'll start with some basics. We'll look at different techniques for displaying the content, how to interact with the content, the hardware that is necessary, and of course speak a little bit about what we expect to happen in the next couple of years. Now, in order to have any kind of bridge between virtual content and real-world content, scene understanding and environment understanding are really required. They allow us to get information about lighting, about the environment where the content is located, and also some really important spatial information. And there are really two different ways to approach this. Of course, the best solution is if we adopt both of these ways. But we'll start with exploring the scene from the inside out.
When we collect information about the environment from the inside out, we can place ourselves at the center of it and position light sensors that can cover the entire 360 field of view. In order to achieve that, we probably need multiple ones, because there is no single light sensor that can, or camera, that can do that, cover the entire field of view. We can then project the collected data onto a sphere that has the same center and a very large radius, possibly infinitely far away. Here's an example of the data collected from a single camera. So each camera collects just a piece of the scene, and then we need to stitch these images together.
So really what we just saw is the basics for 360 photos, for example. It's the same mechanism that is adopted. What the image that we looked at is an example of what is called equirectangular projection. And here is how the image looks when it's mapped from that sphere into a rectangle. Longitude and latitude are mapped to XY coordinates. So there are some things you can notice here. Like, for example, on the equator, there is some information loss, and up to on the poles, there is too much repeating information about things that are maybe not that important. So equirectangular projection is definitely not the best one. There are other ways to achieve the same effect, and instead of a sphere, we can use a cube map, or what is called a skybox in the gaming industry, for example. And it's really just the same idea. Instead of having a sphere, you produce images about the different sides of a cube, and the only difference is change in shape of where you're mapping. Now, in 2017, Google came up with a different projection, which is the equiangular cube map projection. And it's the idea of this new projection is to preserve as much information possible and also distribute it equally into the image. How we can capture these images? Of course, we can use a 360 camera, which is the same mechanism we looked at in the video. But a drone can also be used to achieve 360 photography. The idea is that you can automate the flight of a drone, position it wherever you think is appropriate, and take pictures as you rotate it around the y-axis. And of course, you can use existing apps. Many mobile phones today have that functionality natively to take, for example, panorama pictures, which are a form of 360 images. But also applications like Google Street View allow you make use of all the sensors on your phone to take pictures from different angles of the scene. We can also manually take the photos, but then stitch them with software. And it's not actually computer vision libraries like OpenCV have everything that is required to achieve an appropriate stitching. For example, given an image, you can locate all the features and extract key points from the image. And if you do that on two similar images, you get the same key points on the images, and you can map from one to the other. So you can really attach different images together. How can we display these 360 photos? Well, of course, for JavaScript, you can use Three.js, following exactly the same process we saw in the video. So really just create the sphere geometry and apply the image as a texture to the sphere. And I also speak a lot on different events about A-frame. I really like the framework. I will share some links at the end where you can look at the same effect achieved with A-frame. The idea is that you can map an image, you can specify the image as an attribute to an A-frame component. But what we always do, or what I always end up doing, is adding React as a framework to A-frame and use them in combination. And this is why this time I want to actually look at React 360, which is a framework very similar to React. Actually, it's more similar to React Native, if you're familiar with that one. Uses the same concepts to achieve initially 360 images in the web, but also virtual reality experiences and augmented reality experiences can be built with that framework. Let's look at how you can create a dummy application. So if you use npx to run the React 360 CLI script, init script, it's going to create a new directory. You go in there and you can, there is a start script that is expected to open the browser, and what you would see in that case is the dummy scene for React 360. So what you can see here is a button, small rectangular background behind it, and also an environment background. This is what an empty application in React 360 looks like. And this is the background that is that we just saw in that scene. What you already understand is that this background uses equirectangular projection. And React is really smart. React 360 is really smart about it, as it understands the type of image based on resolution. Let's look how this scene is composed. So we import React, and then from React 360 we can import components which are really similar to the components in React Native, if you're familiar with that. We have a text, the Welcome 360 text. We have a view that wraps the text, and we can also use style sheets. App registry is used to register the modules. Here is the Hello 360 component. So a couple of views used for layout, and finally the text we saw. But if we wanted to change the background to something else so that we can use our own 360 pictures, we need to import environment and asset. We can resolve the path to our photo and set it as a background image. And we can do this with out of the box with most 360 projections. As you can see here, I can interact with the picture, rotate and look in all directions I want. So you can see that it's actually pretty easy to get this behavior out of the box with React 360. But React 360 images are more than just photos and videos. In fact, you can use these assets to create environment maps, which are heavily used in games and 3D content. So, for example, you can use them as a background to a 3D scene, but also they're heavily used for image-based lighting, where the 360 image mapped to a sphere is used to provide information about reflections and lights in the scene. And there's also the other way to understand environment and scenes, which is what I call outside in. Now, it's not outside in exactly, but you'll see in a moment why I prefer this term.
When we explore an environment from the outside in, we still keep the same concept of the sphere. But this time our cameras are placed on the faces of the sphere. This is why I prefer to call it outside in, because the subject of interest is placed at the center of our scene. And the cameras actually don't need to be exactly on the faces of the sphere. It's just important that they don't overlap with the subject.
This process is generally called photogrammetry. It's used to extract information about objects in a scene, do some calculations based on that information to infer new things about, understand new things about the scene and the environment. How we can capture this information? Different hardware can help us definitely. What we saw in the 3D video, of course, is easy to achieve virtually because we have all the necessary information about the entities in the scene. But in the real world, we need some help from hardware. So, for example, we can use stereo cameras. The idea here is that we understand perfectly what is the distance between the two cameras, and then we can triangulate and infer the position of objects in the scene. We can make use of GPS and satellite data. That is always useful to have approximately good positioning information. Of course, it's not the most precise method. And of course, accelerometers and inertial reference systems like gyroscopes always provide very useful information about the changes in orientation of our cameras, for example. Last but not least, we have LiDAR, which is frequently used for 3D mapping objects in the real world. Combining all of these together can yield some very nice results. But you might say, wait, that's too much hardware. And I can provide you with a counter-argument. If you're all familiar with this device, it's the new iPad Pro that's out this year. And you can, if you look at the back on the sensor array, you can notice a couple of things. First of all, it's full with stuff. And the other thing is that it has more than one camera. We probably have all the necessary information about these cameras because we know the vendor and we know the hardware. And the thing you can see on the right is actually a LiDAR sensor. This is the first mobile device to have a LiDAR sensor in it. How that works is that light is emitted from the sensor, and there is also another one that receives and times the light that comes back to the sensor. So really you can achieve a lot with just using iPad and ARKit and RealityKit. So let's look at some examples. So first, let's look at what we can achieve using the LiDAR sensor behind. As you can see, with ARKit and RealityKit, we can actually start getting some more depth information about the scene. Objects you see here on the screen are darker if they're closer to the device, and they're whiter, brighter if they're more far away. Now let's start combining that LiDAR information, that depth information, with the two cameras on the device. And if we do that, we can start locating points in 3D space, actually recreating the scene in 3D. This is what actually happens under the hood in most AR applications today using this technology. So what you see here is not just the output of the camera. This is the actual output of the camera, but it's a 3D model that we can also rotate. Combining all of this information together, we can start treating this real-world scene and as a virtual one, similar to what would be represented in a game world, in a 3D game world. And this is also an environment that we can interact with. So meshes in here and vertices are colored differently based on where their location is. Red means that they're closer to the camera, blue further away. So we can start positioning things. For example, if I click here, I can place a sphere. The shape is being understood as a wall. And you can see that physically also collisions worked with the real-world environment. Another thing is the new 3D format, USD, created by Pixar. It is different to other formats in that it has been developed with multiple iterations, I think 4 until now, until all the requirements were satisfied. So this 3D format is a container for entire scenes, and we can actually use this today on the web. If you see this icon on some website, it means that AR quick look content is provided, and we can, if it's a product that we are looking at, we can usually import that into our scene and inspect the product closely. So this is the state of the art of augmented reality. But of course, it's not the end. Much is happening in the field, and we expect a lot of new things to follow. A small spoiler alert. The AR market, for example, is expected to grow 4 to 5-fold in the next 5 years. So that's a big motivation for companies and developers to enter the field. Just like with LiDAR, better and more available hardware is becoming available on different platforms. Hopefully one day this will be available on the web as well, and not just on mobile platforms. And I'm saying this, of course, as a JavaScript developer. And finally, we can expect to have much more improved software, especially with the help of machine learning. I'm also actively involved in the field. We are trying to achieve much better object segmentation and actually 3D reconstruction, approaching this problem using machine learning from different angles. This presentation would be available at this link. And if you want to know a little bit more about 360 images and the problems that are being solved in there, please just change the path to IMPROC 360. And if you're interested just in image processing in general, you can check out the other presentation, which is IMPROC WASM. Everything is written in C, and the code is run in WebAssembly for simplicity. Thank you very much.
Hello everyone, my name is Samuil. Today we will talk about modern event-driven systems and see how we can apply them in practice. So we'll first start with the main concepts of event-driven systems and why we need them. You know, modern system requirements are changing constantly, and modern software becomes highly integrated across enterprises, and business needs to support innovation in order to be competitive and even survive. So nowadays we have requirements for systems to be highly available, being real-time. They need to scale globally across multiple countries, across millions of users. So event-driven systems is a way to achieve all these kind of requirements, which we'll discuss a bit later in our talk today. Especially event-driven systems are used in cases whereby we need to apply analytics and machine learning in integrating mobile and IoT, of course monitoring, real-time and fraud detection. When we have like some interactive web and embedded devices, unfortunately these are out of scope of today's talk. So when we talk about event-driven, we'll mostly discuss integration that is happening between different components inside a distributed system. Usually an event is created as part of something that happened, like a mouse click or even a hardware interrupt that occurred and being recognized by a process, by a software. And then we usually listeners register them to the source and receive these events. But events are usually carried in event-driven systems over messages that allow inter-process communication. And a message is a means of exchanging information between different processes, whereby we just have an addressable recipient. So nowadays we have mostly two types of messaging integration, brokerless one and with a broker. So brokerless is usually much simpler in terms of topology. We just have a producer and consumer, and then they can integrate with TCP, UDP or shared memory. And of course we can have multiple consumers in some cases whereby UDP multicast is allowed, or we can integrate them as well with shared memory. Such kind of libraries are, for examples, are ZeroMQ or Aaron, and these kind of brokerless messaging tends to be very low latency oriented, and because of lack of mediators and because of low level optimizations. However, more often they are not very suitable for the cloud, just because they have very specific deployment requirements. For example, UDP multicast might not be allowed in public clouds. Nowadays we also have other integration protocols like RSocket or Socket.io. They're especially intended for peer-to-peer communication. And the good part here is scalability is improved because we are just transferring this kind of concern to networking level. But with message brokers we can achieve much more, and they can solve a wider variety of problems. In our case, we just have a broker that decouples producers from consumers, serving as a mediator, and a broker can do lots of stuff, like for example publish subscribe. It can just broadcast single message to multiple consumers, so each of them can receive the same copy. We can of course utilize queuing, whereby competitive consumers are load balanced by the broker. They just get their own parts of the messages inside a queue channel. And even routing, whereby the producer is not aware of where the messages would be sent, and this is something that the broker is interested in, so it can route messages to different consumers based on some message headers. Example of message brokers are nowadays the most popular ones are RabbitMQ, ActiveMQ, for example, NUTS. Of course, on the cloud we have also message brokers like AWS SQS, and a part of what we already listed here. They provide, for example, some features like message validation, aggregation, and transformation. Exclusive consumers are used for failover, and they also differ in delivery and ordering guarantees, which we'll come back to later. From then on, at later point, there's another concept that evolved, the distributed locks. The idea here is very simple. We can just model a lock being append only by producers that write new events to it. And then we can have consumers that are actually preserving their own offset from whereby they want to read from the lock. And whenever there's a new event available, the consumers would receive it. It turns out to be a very simple concept, yet very powerful, because it offers much greater scalability and throughput, both for producers and consumers. Unfortunately, this is not very low latency, but it can serve a wide variety of problems. And because data can be read multiple times, we can keep historical data there. And this is very powerful in modern, highly integrated software. Usually these distributed locks offer very high availability and reliability, as we'll see later. This, for example, Kafka or Pulsar on the cloud, Google Cloud pops up, or Amazon Kinesis are specific examples for this kind of distributed locks that can serve as a message broker use case scenario. And on top of this kind of distributed locks, nowadays we have stream processing platforms and frameworks. The idea here is very simple. We can create a platform that can be coded in very high level. It can consume streams in real time and produce other streams again in real time. This way we can code in very high level how we can process data. And lots of big data solutions nowadays are used to build such kind of solutions using stream processing framework. For example, such kind of transformations that can be applied would be stateless one, like map filtering of events. But of course we can apply much complex transformations that are stateful, like joining multiple streams into single one, or windowing, whereby emitted events are just aggregated for a specific window in time and then broadcasted to the new stream. There is also a wide variety of stream processing platforms nowadays. They vary between their deployment options, how they are declared, like how the processing is being configured or declared via code with APIs or some kind of configurations. We can also adjust micro batching or event by event processing, respectively, for high throughput or low latency. They even provide SQL like definitions and can integrate with database sources files. Of course, they also differ in guaranteed delivery, which we'll come to later. So before we actually explain concepts like guaranteed delivery, we should first be aware of how consistency plays a major role in modern systems, modern distributed systems, and especially in event-driven systems. For example, first of all, we should just imagine the case how we integrate systems with event-driven style. We have consumers and producers, but the flow of data is inverted. So the consumer would just receive new data whenever it's available from producer instead of asking for it. This is huge change in the way we create software, because now the data flows through the components, but it needs to be cached in order to retrieve at later point. For example, if we have client integration which uses some kind of RPC, we need to cache the data somewhere, either in database or in memory, in order for it to be available for reading. But it also has the benefit in terms of performance, because data is now available for reading and reads are very fast. So when we think about consistency, one of the major roles of how we imagine it nowadays is the CAP theorem. So it states that we cannot achieve availability tolerate partitioning, network partitions, and achieve consistency in terms of all clients see the same data at the same time without sacrificing one of these three. And in event-driven system, we usually tend to build systems that are eventually consistent, but they offer much higher availability, meaning that the function of the software could be executed even if not working on the latest information. For example, think about a client that can try to observe state in both the producer and consumer. We have also broker as a mediator. In the same time that these requests are executed, we might have inconsistency because the consumer hasn't applied yet all the changes that have been received from the producer. But this kind of model is very performant just because if we have, for example, a broker and it would degrade much better compared to RPC style when there's a lot of writes, just because a slow consumer would be protected by the broker from spikes in the load, and it can tolerate much better such kind of oversaturation coming from fast producers. But this is of course a trade-off in terms of consistency, because the client wouldn't get the most recent data, especially if the consumer cannot catch up with the producer. And it also plays a major role in availability, being a lot more fault tolerant. For example, the consumer doesn't need the producer to be available in order to still operate and execute its function, because anyway it's obliged to cache the data that's needed for later retrieval. And also a consumer might not even need, or the producer might not even need a broker, which we'll see later, because the broker not being available means that we can still have a producer and consumer being able to operate and catch up with data not being sent at later point. And yet another complexity that we need to trade off for this great benefit is out of order processing. In such kind of event-driven systems, they're usually asynchronous, meaning that we can receive data out of order. For example, if we have a delay somewhere on the network path, it might come out that consumer receives data not in the order it expected. So most implementation need to consider this. There are solutions nowadays. We can use inbox pattern, or we can just use versioning in order to protect consumers from such kind of anomalies. And another trade-off here is how we play with delivery guarantees. Ideally, a message produced from producer and sent to consumer can fail anywhere at any point, either in producer before it's sent, or somewhere on the line being sent in the broker, or even when processed by the consumer. So nowadays we have this kind of delivery guarantees at most once, at least once, exactly once. They usually involve state. In the very simple case, it's very fast and cheap, where we don't have a guaranteed delivery of messages, but it's not reliable. If we want to have at least once delivery guarantee, the consumer might receive a message more than once. This is usually okay. We can protect ourselves from consumer perspective by using patterns like idempotent processing or inbox deduplication, and the producer state would just retry until the message is successfully delivered. For exactly once, we also need to have this kind of inbox pattern for sure. So one of the most applicable scenarios for event-driven is actually combining these architectural styles, event-driven and microservices. The great thing about microservices, again, this kind of inverted flow, which means that each microservice can operate its own logic and doesn't need to query other services to maintain the logic usually. And what is more is that services can replicate the data they need. from other services and execute their own workflows. Also, this is great for local development. You don't need to run huge amount of services in order to execute some kind of business workflow. You just need a broker and a single service you can focus on. And microservices is all about encapsulation, just because we can have different teams working on different microservices, so they all need to be independent. Nowadays, this is achievable using domain-driven design, but it turns out some process needs some integrations between services, and it comes out that standard messaging is still not great, but if we use stream processing with Kafka, this is great for us because we can we read historical data. For example, we can add the publisher changes before the consumer is ready to receive them, and then the consumer can read the historical data and catch up. We can decide at later point of the life of the system to add a new consumer. We can join streams and create newer ones, having a centralized data, which is usually anti-pattern in microservices, but we are okay with distributed lock just because it's not a single database, it's not leaking private models. And the way we model events is also important. Usually we have two types of events modeling techniques, either notification, which are more or less showing a business intent, or event carried state transfer, which actually is more like event describing what kind of updates have been added to our models. Then based on this, we can actually achieve a greater step in how we integrate microservices. It's called event sourcing. The idea is very simple: treat all entities with their life cycles, like a list of their life cycle changes. This way we don't need to preserve the last state only, but we can also have like audit log of what happened in the system. We can enhance this way the security. We can easily do time-based queries, so we can get the state of an entity in the past, and it's much easier also to fix issues. And we can also treat distributed log like Kafka in the same way that we treat an event store. We can use it actually for this purpose, and this way we can have materialized view otherwise over data that needs to be queried, which is the later pattern called CQRS. So it tries to solve the idea how when we use event sourcing, how we get the data in some state that could be easily queried by clients. So we don't, having the event store, we can reconstruct an entity in multiple ways, and that's brilliant because we can have, for example, Elasticsearch to query the data in a way that we can do a full text search, for example, in the browser, or we can have like Neo4j, which is a graph-oriented database, especially for social networks interactivity and so on. We can even populate caches based on events that have been published from services that own the data. So now we come back to the business workflows and the single writer principles. So here we have each microservice encapsulating its own workflow with its own models, and these models are actually replicated over other services, and based on them they can manage the data by using what has been already replicated. Usually most systems tolerate this kind of consistency. However, if we need something more complex, we need to deal with distributed transactions on application level, which is also possible with event-driven systems. But they're much more complex to implement, and they're out of scope of what we'll discuss today. And of course, we can even treat databases as a stream of events, just because each transactional database nowadays has a so-called transaction log or journal, So this is where all the changes are being written ahead before they are normalized in indexes, and usually we can subscribe to these changes and grab them. We can export them to like distributed log like Kafka, and stronger microservices can use these kind of events to reconstruct the models in a new way, whatever it would be needed to be used in the new microservices systems. And the great thing is we can operate the new microservices together with the old ones seamlessly, and if we decide to disable it, we can just stop the monolith functionality and switch to the newer microservices by keeping all data in sync. And event-driven is also changing other aspects of software that we build today, like web and mobile. Think about, for example, real-time updates that we want to receive, like dashboards or stock prices being updated on our screens. So this kind of data is changing very often. It's usually very convenient to have this kind of data being sent as in an event-driven way. And we can build architectures based on combining server-sent events or HTTP long polling techniques with long-lived HTTP connections to our application servers that are serving as mediators in the backend. And the application server could easily read from a streaming platform or a distributed log to catch up with historical data, sending it to devices that have fallen behind. And also this can seamlessly work for offline mode, just because the devices would always receive the latest data whenever it's available. So if an application needs to operate offline, it would have all the data that it needs at disposal. In similar fashion, we can implement web push mechanism to broadcast any notifications to mobile devices or to in-web browser. And event-driven is also great if we want to build some kind of real-time interaction between users. Think about multiplayer games, think about collaboration tools like Google Docs, think about chat. So all of them could be easily done with event-driven systems. In our case, here you can see an architecture whereby edge devices are connecting to some kind of web server, and this could be easily created with actor model on the backend, for example, to receive events, to initiate the game state in case we have a multiplayer game. And players can just send as events their actions. The game server could control, validate where their actions were correct, and then it can broadcast all the game state changes that needs to be displayed on the screen. And this is great. We can even use some kind of already existing messaging protocols like MQTT when we deal with mobile devices. Think about chat. This is a great option if we also want to have very low power consumption. And when we think about big data, streaming is a great option to implement it, and streaming is built on top of event-driven systems. For example, we can implement real-time ETLs, replicate data from existing databases live, and do any kind of stream processing. We can even use standard JDBC or ODBC APIs to get all historical data and put it into a stream processing framework that would denormalize the data and put it in other databases that are especially optimized for specific use case scenarios like analytics or any kind of relational workflows. And we can even capture files, for example, that are uploaded to SFTP servers or that are uploaded in storage on the public cloud. Once we capture new files, when we receive events or we listen on the file system, we can then split the file into multiple events that could be then processed by the stream processing framework. Of course, IoT is another great example of how event-driven is used. Think about low-power devices for like smart city, smart home, like car networks, for example, that send live data, telemetry about what's going on inside them, or send live statistics. We can use any kind of bridging technologies like MQTT or even HTTP with serverless, that's event-driven oriented, and then we can use stream processing frameworks either on the cloud or on premises to build sophisticated like analytics, or we can even combine them to some kind of machine learning that would be bidirectionally update and reconfigure devices if needed. And machine learning is another great example where we can also use streaming, like in Spark. For example, here in this diagram we can have different variety of sources, and we can train models with live data, like offline training, then deploy the already trained models and use them for scoring. We can also, even some algorithms for machine learning allow online training, whereby scoring and training is happening in real time with real data that's incoming in the system. That's especially great because nowadays enterprise doesn't want to wait for batch processing happening. As you've already seen, event-driven can focus on solving huge variety of software engineering problems. So think about it twice when you are trying to create a solution. Thank you very much.